Understanding linear regression is important because it's one of the most popular, simple, yet highly powerful tools for making predictions and uncovering patterns in continuous data. So let's move straight into an example to explain how linear regression works. A simple linear regression is a statistical method that helps us understand the relationship between two variables, and then to make predictions about one based on the other. Let's say we have data on houses, including their size and price. Let's plot those two variables on a chart. Now, let's say we have a new house that we know the size of but not the price. We want to use the size of the new house to make a prediction on the likely price using a linear regression model. So let's do that. In this case, the house sizes in our data would be called the independent variable, which is a variable we use to make a prediction. And the house prices in our data would be the dependent variable, which is what we're trying to predict. So what we use a simple linear regression to do is to draw a straight line through the data that enables us to make our informed predictions. So if we have our regression line that best fits the data here, we can use this regression line to make a prediction of a new house price based on the new house size. For example, if we know the size of the new house is 2,140 square feet, we can use a linear regression model to predict that the house price would be around $300,000. We have used our independent variable of house size to predict our dependent variable of house price. So those are the absolute basics of how a simple linear regression works. So how is this regression line created? The regression line is determined using a method called least squares, which minimizes the total square difference between the actual data points and the line itself. These differences, known as residuals, represent the distance between the data points and the regression line. The goal of the model is to find the line that makes these residuals as small as possible, resulting in the most accurate predictions. This regression line can actually be described in a simple equation, and that equation is y equals mx plus b, where y is the predicted value, in our case the predicted house price, m is the slope, which shows how much y, price in this case, changes for each unit increase in x, house sizes in this case. X is the independent variable, house size in this case. B is the intercept, which tells us the predicted value of y when x is 0. Now, of course, in this case, a house size of 0 isn't realistic, but the intercept gives us a baseline for our model. In real-life scenarios, we often focus more on the slope, because in this case, the slope tells us how the price changes based on size, which is the insight that we're really interested in. But how can we measure how well our regression line fits the data? That's where the R² value comes in. R² tells us how much of the variation in the dependent variable, house price in this case, is explained by the independent variable, house size in this case. The R² value ranges from 0 to 1. An R² value of 1 means the regression line perfectly fits the data. A lower R² means there is more variation in house prices that our model isn't capturing. In simple terms, R² just shows us how well our model explains the data. The closer it is to 1, the better our predictions align with the actual prices. To calculate R², we compare how much of the variation in house prices is explained by our model versus the total variation in the data. So in this case, we can see that the price of a house isn't entirely explained by the size of the house. Otherwise, the R² value for this model would be 1, and the points would fall perfectly on a straight line. Other factors like location or the number of bedrooms might explain some of the remaining variation in price that our simple model isn't capturing. So remember, the closer your R² value is to 1, the better the model fits the data. So in summary, simple linear regression helps us predict one variable based on another by drawing a straight line through the data, represented by the equation y equals mx plus b. The closer the line fits the data, the higher the R² value, which tells us how much of the variation in the data our model explains. Now, this is just simple linear regression, where we use one variable to predict another. But in many real-world situations, one variable isn't enough to make accurate predictions. This is where multiple linear regression comes in. In multiple linear regression, we use more than one independent variable to make a prediction. For example, we would predict house price based on house size, number of rooms, or even factors like proximity to a school or the year in which the house was built, etc. The idea behind a multiple linear regression is the same as a simple regression, but now instead of a single line, you get a more complex model, sometimes represented as a plane or even higher dimensions. In multiple linear regression, the R-squared value works the same way. It shows how much of the variance in the dependent variable is explained by the model, but now it reflects the combined impact of all the independent variables. So if we use both house size and number of bedrooms, the R-squared value will tell us how well these two factors together explain the variation in house prices. In multiple linear regression, the equation line is expanded. Each x represents one of the independent variables, like house size or number of bedrooms, and each m is the slope associated with that variable. These slopes show how much each independent variable affects the dependent variable, in this case house price. The intercept, b, is still the baseline where all the independent variables are 0. By including multiple variables, the equation helps us capture more of the factors that influence the outcome, making our predictions more accurate than a simple linear regression. I hope that this simple explanation of linear regression has been helpful. Remember to like and subscribe for more, and I'll see you next time.